Hello and welcome to section 4 of the training recording of the Academy course on Voice over LTE radio planning and optimization. My name is Benedikt Aschermann and I will be your moderator for this session.
Hi, my name is Charles Libby.
So Charles will be the main speaker of this session, and he has all the technical competence to properly address any topics. As you can see from the agenda of this session, we focus here on voice over LTE specific features which intend to improve the network performance and or the user experience when using voice over LTE. Charles, perhaps you want to give us a short introduction about each feature, and then we drill deep during the section.
Well, in this module, we're going to look at what is robust header compression, how do we use it to optimize the air interface for voice over LTE. We'll look at the uplink and downlink packet segmentation feature and the TTI bundling feature, which really are very much related between the two of them. But the whole idea is to make sure that we have a good way of delivering our packets to the subscriber, or the packet delivering the subscriber delivering the packet to the network in a way that is with confidence. We'll look at the smart DRX functionality as well as things that we can do to help improve our voice over LTE talk time.
All right, if we now look into the first feature, robust header compression, the intention of that is mainly to reduce protocol overhead. Why is that so important when dealing with the voice service?
Well, in robust header compression, what we're doing with it is being able to take the headers that are above the LTE section, above LTE, so we can come here to the payload, our payload. Let me go ahead and give you a way to point so you can see it a little bit better. We have our regular payload of our voice, but in front of it are different headers, like the RTP header, as we saw in Module 2, and the UDP header, and the IP header. Now, the example we're showing in this picture here is an IP version 4. We do support IP version 6, but the idea is to be able to compress those 320 bits of header, IP, UDP, and RTP, into 40 bits of actual transmitted data. Now, this is really to help reduce the number of bits we transmit over the air, therefore maximizing the amount of payload we can get through in the minimum amount of radio resources.
Okay, I see. So shall we move on to look into the feature details then?
Sure. Our robust header compression really works in an interesting way, in that what it's doing is each end of the packet of the flow, I'm going to have a packet flow that starts from the network or from the subscriber, and this is true in either direction. So this is not a one-way reduction. This actually reduces in the uplink as well. So robust header compression occurs in the subscriber and in the eNode B. So we have this packet flow. I'm going to show you the downlink version. And the downlink will compress the header. We'll set up a context for that header compression. We'll reduce the headers. We'll compress the packets and then go ahead and forward it. Now this is going to be, we're going to refresh this on a regular basis. At the other end, we will have a decompression of headers. We will have collected the context before we start. We collect the context and we decompress the headers, and the header comes out. Now, if there is an error, there will be feedback, or we will have periodic feedbacks where we send the full uncompressed to verify that we still have proper context. And I'll get to that in a little bit.
I understand that this is like a multi-stage process, and it's increasing the degree of compression gradually. Would you explain some more about this specific process?
I like to draw this in a triangle, in a way. This is a very good statement of what's happening. So the initial stage, and I'll tell you why I draw it in a triangle in a minute. So in the initial stage, I take it and I use I have initial compression. There is no compression initially. There are no static fields that are being monitored, nothing. I'm going to go ahead and initialize a context. I'm going to monitor the static fields in the headers, things like the IP address. I'm going to create an index for those IP addresses, or a table for those IP addresses, and replace it with an index number. So that's where I'm developing a context. So that's my initial context that is being developed to create a static context. Now, when both ends have agreed to have reached that point, they have reached a static context, they have the static context in place, then they will move. There will be feedback that says, let us move to the first order. Now, in the first order, we begin taking the IP field, for example, and we set it to index number 1 for source and index number 1 for destination. And that way, instead of 10.1.1.5 and 13.2.4.6, and I'm just coming up with numbers, you have index 1 source, index 1 destination. And that becomes the first order. Now, that means we've compressed from 32 bits down to whatever, and we'll see the parameter later on, to 2 bits, from 32 bits to 2 bits for one IP address. Now, at this point, we start learning the patterns of the dynamic fields. So we're going to start looking at dynamic fields. So, for example, there's a sequence number that appears in the RTP header. There's the timestamp in the RTP header. So there's several different things that we can use. But these are dynamic fields. They constantly change, but they constantly change in a consistent pattern. So it is a persistent pattern. So a sequence number increases by 1. So it would be increase of 1. So x plus 1 would be like a formula that would describe that particular sequence number. The timestamp is x plus 20 milliseconds. So therefore, you know that it is always going to increase by 20 milliseconds. So we store that and create a context. This is the full context. We create a context of an additional set of contexts for the fields that are the dynamic fields, sequence numbers, timestamps that are consistent. And again, that are consistent. We're looking at consistency ones that we can predict. So we create that setup, we create that context, and then once both ends, this means that the subscriber and the eNode B are doing it, we will then send feedback and move to the second order. Now here's why I draw this in a triangle. If at any time in this whole process we ever end up with an error, there will be feedback from the end where the error occurred, and everything moves back to the initial stage of it does not go backwards down the list. It will always, so if an error occurs in the second order, we move straight to initialization. We move straight back to uncompressed state. If we have a problem in the first order, we move to uncompressed state. So it's always moving. And this is one of the reasons I draw it in a triangle, so that we can see that from the second order, I don't move back to the first order. I will always revert to the uncompressed state for recuperation after an error.
Oh, okay, so here we have an example of how it actually looks in terms of IP packets. Would you tell us some more about this?
And yes, this is a good example of what we're doing. So in the uncompressed state, here I have this 32 bits, and I have a sequence number, or I have a dynamic field, or yeah, so I have a dynamic field of some kind, and then I have the MAC header and the RLC header. So this is the packet part. So what we do is we'll take those and we'll give them say there's an index number here. We'll just get an index. We'll create an index set, and when we transmit it, we actually transmit it without the header, but just with the index. So we assign an index number to each particular function, and we put it into and transmit it in without the headers or with a reduced header, so that when it gets to the destination will be able to know, okay, well, this was packet 3. It's going to have a 10.1.10.0.1.10 and so on for each one of the packets. So it knows, okay, this is the index we're going to use for this header. So in the compression, in the sending, we actually put an index in instead of that field. That way, and I like to draw this out in many ways, but that way the context, when it gets to the subscriber, it's actually going to be with just an index. Then the subscriber will rebuild it based on tables that it contains.
Okay, well, that seems clear enough. What do we expect in performance when applying this feature?
Well, that's a great question. We actually decrease the throughput required by one subscriber by about 46%. What that means is I can put more subscribers in. That means, or we can have better voice codecs that are used for each subscriber. That's a real benefit. That means I can do more calls simultaneously versus subscribers that have, or we have better calls, so we have better quality. Another thing is, with the robust header compression, it allows us to use a lower MCS, which is a more robust MCS, but in that means because I'm transmitting fewer bits, I can use that to also provide a better coverage of my cell. It gives me about 14% larger cell range in robust, by using robust header compression because of the higher or the lower MCS or the more robust MCS.
Yeah, that's impressive. Actually a good example of what you can gain by doing things in a smarter way. I see those parameters here. That looks pretty straightforward. Is there something specific to mention about these?
Actually, there is. In here, first of all, we have to activate it. That's pretty straightforward. We either have it or we don't have it. We activate it or we don't activate it. Now, there is something that we do need to be aware of is, remember I said there's an index, and how big is the index? Well, the index is set by this parameter here. So how big is the index that I'm sending? If I only have 4 contexts, that means I can compress that header for 32 bits into a header that will contain 4 contexts, which would be 2 bits. Therefore, I can take 32 bits and compress it to 2 bits because of the 4. But I set that context here. So the smaller this number is, the more compression I get. The bigger this number is, the less compression I have for the fields. But the more robust header compressions I can enable. So this is a trade-off, but it's the index size of the field. It's the size of the index used for those fields.
So I think we are there to move on to the next feature. It's the controlled uplink packet segmentation. Charles, please move on.
All right. In controlled packet uplink segmentation, one of the things that we're doing is and this is uplink. Notice that this is dealing with the uplink segmentation. This is a feature that is automatically used in the network to adjust for the subscriber being able or having poor coverage. Literally, we are limited in coverage. We are limited in throughput. We are limited. Oh, sorry, that was not intentional. We are limited in coverage because we've reached the limit of our coverage from the standpoint of what is the lowest MCS we can go to and what is the amount of resource blocks that we have, so the maximum number. So we've reached the point where a regular call, a packet that's a regular packet, cannot be sent without breaking it into smaller packets or smaller segments. Now, our scheduler will do that automatically and will enable a breaking up of a packet into smaller packets. Now, what this does is it allows me to send the same, so here's 304. If I break 304 into two parts, then I have 152 bits and 152 bits. The only catch is I have a little bit more overhead. I have higher overhead that's involved here because I'm sending that packet in two consecutive transmissions. So it's two different transmissions. But the area that I have available is more energy, meaning I can reach the site or I can extend further and further out in the cell. This allows the subscribers uplink, which is our biggest limit, to be able to communicate better in the uplink in spite of poor coverage. It allows it to communicate with the eNode B effectively.
All right. So then we would also like to see how this is showing in the lower levels of the air interface. I guess there must be some impact when doing this kind of segmentation.
What it is I do have an increase in overhead. There's a couple things that are increased in overhead here. First of all, I'm going to have more headers because every single transmission, so even though I took a packet here and I subdivided into, in this case, up to 4 packets, I'm going to have a MAC header, an RLC header for each one. I'm going to have a CRC. That's extra overhead. I am also going to have a PDCCH assignment in each subframe. Therefore, I'm using more PDCCH resources. I am using more bits of transmission over the air, but because I have better power availability for these transmissions, I actually have better coverage. So the cost is more bits of cover, more bits of use for the actual transmission, more PDCCH resources, more hybrid ARQ resources because I will have to acknowledge every single packet. So if I don't get it, I have an ACK. I will have to retransmit that and retransmit until I get an ACK, which in essence means I'm using more resources of the ACK-NAC functionality.
Okay, in this context, then it could be interesting to see the actual numbers. How much overhead do we add for the sake of coverage?
Right. Right. The overhead for this, if we only have one segment, so we break it into 2 parts. we take that segment and we're going to add 40 bytes or 40 bits of header. It's going to have the whole number of bytes that we're transmitting is 328. That's 12% overhead. So this is a single segment if we transmit it as one. So we have the 40 bits of header, we have the total of 328 bytes, so we have 12% overhead for a voice packet of 288 bits. So these are in bits. Now if I break it into two parts and I break it so that we can transmit it, I'm still transmitting the same 288 bits, but now I have 80 bits of header, meaning I have 368 bytes total, giving me a 22% overhead. If I break it into 4 segments, so now I'm breaking it into, so I'm taking that single packet, breaking it into 4 parts, that 288, so now I'm going to have like 122 bits per transmission. That means I have 160 bits of header. That means my actual transmission is around 448 bytes of total transmission in all 4 segments, giving me a total of 36% overhead. That's a lot of overhead just to make sure that the subscriber receives the packet or can transmit the packet in the uplink. Now, again, that does not include, this is one PDCCH assigned resource, this is 2 PDCCH assigned resources, and this is 4 PDCCH assigned resources. So I use the PDCCH, the physical downlink control channel, a lot more.
Okay, so then we are down to the related parameters. Looks like
no, there's not too much on the parameters. Not too much parameters though. All really we're going to do is we set what is the minimum size that we're going to block, what is the smallest transport block that we can use, and what is the minimum number of resources that the subscriber will use. Now this is how we do segmentation in the uplink. And this is going to be true of pretty much any type of packet. This is not just dedicated to voice.
Very well. Another one gone. Let's move on then to TTI bundling. What I understand, it's a bit more complex. Well, there always should be good reasons for introducing complexity. What's the reason in this case?
The reason for TTI bundling, in this case, is actually going to be helping me ensure I have better coverage, similar to robust header compression, or similar to, to uplink packet segmentation. TTI bundling is a related feature. In fact, the two of them look very, very similar. We have to be, what we're doing here is we're finding a way to do the transmissions and the retransmissions. And so what I'm going to do is I'm going to step back just a little bit, and let me go back to this diagram. This is the controlled uplink packet segmentation. In hybrid ARQ, I'm going to have NAC resources that are used, and I'm going to have retransmission, and I'm going to have all of these that may be retransmitted or not retransmitted. And this is only revision 1, or this is revision 0, and the retransmission would be revision 1, and the retransmission after that would revision 2 or 3, whatever happens to be the order we use them in. But in TTI bundling, and I move back to TTI bundling, we have hybrid ARQ retransmissions that use up resources. We also have the RLC segmentation. So from the segmentation standpoint, we're going to be using the hybrid ARQ and segmentation. We're going to be using this to improve that uplink packet segmentation. Again, TTI bundling is only in the uplink. Now, we can enable it for other capabilities, but in Nokia's implementation, we are specifically limiting it to VoIP users, but it is not just limited to VoIP users. We can use it for other things. Okay, so there are some drawbacks to the type of things that we're doing with the hybrid AirQ and the segmentation. We end up with more delays. We have longer, more overhead, and more control signaling. So what we're doing with TTI bundling is helping to reduce that overhead and overload signaling. So what we're looking at in TTI bundling is to gain some kind of functionality that will give me something like what uplink packet segmentation is, but more reliable with less overhead in the control functionality.
All right, this sounds quite promising. I guess there is still some price to pay for the improved coverage here. So I guess we'll learn about that when looking at the details of the feature.
That's probably the best place to look at it. So one of the things is TTI bundling is not in place all the time. I'm using uplink packet segmentation anytime I'm in certain coverage. Now, once I exceed that certain point, I'm going to have a boundary for the TTI bundling. I'm going to activate TTI bundling, and the idea is to make sure I have enough coverage until my handover conditions are fully fulfilled so that I can hand over to a different site because I'm in very poor coverage. Now, what is it giving me? Yes, that price that you pay, it is going to cost something, and as we get into it, we'll see more. It does give me a better cell range, especially for VoLTE users. It does reduce the uplink packet loss rate, and it does cost on cell throughput because it will use more resources, similar to the packet uplink packet segmentation. It will use more resources. So let's look at what we mean. First of all, the subscriber has to be able to do it. So this doesn't work for all subscribers. This only works for subscribers that have in the feature group indicator. Oh, I'm sorry. Yeah, in the feature group indicator, we have to be able to support the functionality. And so this is what we have to have. So in the feature group indicator, and this is in the message that we saw earlier called the capabilities negotiation, we have to have these 3 bits set in the feature group indicator saying it can do TTI bundling, it can support in the RLC a 5-bit sequence number, unacknowledged mode. It can also support unacknowledged mode in the RLC, so the bits 3 and 7 have to be set, and it has to support the TTI bundling, which is a release 9 compliant UE. So not every UE gets to use this functionality.
All right, but it's so that both release 8 and release 9 UEs or later would be able to run with this feature.
Yes, they would be able to continue on.
Are there further prerequisites for using the feature for any given user?
For the user, they have to be in a condition of, the radio condition has to be appropriate. Now, here's the feature group indicator. I talked about it earlier, but this is in the actual message that I was showing, the UE capability container. It shows the feature group indicators, bits 3, 7, and 28 are set to 1, which allows the subscriber to perform the TTI bundling. in the feature to actually perform the feature, that's what the subscriber has to do. The rest of it is actually dealing with the radio conditions. We have to have the right bearer situation. In this case, we have to make sure that we have at least one bearer is configured for TTI bundling support. In our case, that would be a QCI 1 bearer, which has enforced TTI bundling as a parameter. Okay, and this would be in the QCI table or QCI tab for that particular bearer flow. It has to be in, I have to have ERAB. I'm always checking for TTI bundling conditions and bearers when I'm doing my establishment of my call. So during the ERAB setup or release, I will look at the TTI bundling. If I have an incoming handover, I'm going to look at the TTI bundling functionality of the bearers that the subscriber, the inbound subscriber contains. Okay, so I make sure that if it has a QCI 1 coming in, it also would be able to do TTI bundling. And then anytime I do a modification to ERAB, to the bearers themselves, I may have to check to ensure that the bearer TTI bundling functionality is available for the subscriber. If it's not, then I cannot, if it's not enabled, then I cannot do TTI bundling for that subscriber.
All right, so that are the logical prerequisites, you could say. The rest then should be radio conditions. As we said, it would only be applied close to the coverage edge. What are those then?
That's a great question. What we have in the coverage edge is we're looking at, first of all, we're going to use an intra-cell handover when it occurs. Our coverage edge means our subscriber has reached the lowest threshold from MCS. Current MCS is lower than or equal to the EULA low threshold, and the maximum number of PRBs that we have assigned to the subscriber is less than or equal to the EULA low PRB threshold, and the minimum or the minimum, whichever is greater of these two, the minimum PRBs that we can assign to a user, and we have reached the TTI bundling block error rate threshold. In other words, we have exceeded some setting for maximum number of block error rates, or that's the ACT max that we've received. So we have to have all three conditions in, just so that you can tie it back to what we've already looked at. These two are the only two that are used when we're dealing with uplink packet segmentation. Number 3 is the new condition that's added as a part of TTI bundling, as well as the ability to perform TTI bundling. Now, once we've reached these conditions, we have to perform an intra-cell handover. What that means is the eNode B sends a handover command to the subscriber to perform a handover, and the destination cell is the same cell. That means it can now modify the TTI bundling parameter so that the eNode B can synchronize and the UE can synchronize to the new transmission mode called TTI bundling. We do this intra-cell, within the cell, okay? And the intra-cell handover does not rely on radio conditions. It is mostly to make sure that both ends of that communication, in this case the UU communication link, is established so that we can make sure the subscriber and the eNode B are performing the exact same functionality and they are communicating in the same language.
How do these criteria work together? Quite often we have trigger timers when activating such features.
And this is very, That's very true. Most of the time we do. So what we have is looking at our TTI. So here we have our EULA threshold. Okay, this is the low MCS. So sometimes we'll go below that MCS. So equal to or below that threshold is one of the triggers. So this would normally, this is the MCS of the subscriber. So here we are below. We also have the maximum 3RBs. In other words, we have to be below the number of PRBs assigned, below this threshold, equal to or below. In this case, we have it equal to in this particular highlighted segment. This is also our highlighted segment. So looking at this column, we actually see that those two conditions are true. Now, we also have another threshold where this is the block error rate threshold. So we've exceeded the block error rate threshold, and the reason we don't go into TTI bundling at this point is because the number of MCS is below. Okay, that's another true, so it's equal to, but the MCS is higher. So the number of block errors here, or the number of PRBs assigned, is low enough. The error rate is high enough, but the number of, or the MCS is lower, is too high. So therefore it won't go into TTI bundling mode at this point. But where back here, we are actually getting to the point where the subscriber passes that threshold. We are above that threshold, and we're equal to the minimum number of PRBs, and we're below the MCS threshold. This will put me into a TTI bundling mode. So it is a and. At this point, we are going to trigger. So let's assume that the thresholds are the lowest MCS is 1, the lowest PRB is 1, number of PRBs is 1, or the minimum, so it's the bigger of the two of these, is the maximum of the two of these, so 1 and 3. So the maximum of those is 3, therefore the number of PRBs is 3. We are going to have a PRB blur, our TTI bundling blur threshold, so we have exceeded 15% of block error rate. That means I've had 15 NACs out of 100 ACs, or out of 100 transmissions, and I will then trigger the intra-handover, so intra-cell handover, to go into TTI bundling. So we still have the handover to do.
But it's a TTI by TTI decision, essentially. No waiting time or trigger time was involved here. Would you have a practical example for us to see this in operation?
So here's an example. Here we have our uplink MCS that's in place. Here is our number of PRB assignments. Here is the block error rate, and whether I'm in TTI bundling mode or not. Okay, so if we look at it, and it's hard to look at it, let's look at just this particular red line here. So if we'll notice that the uplink MCS is high. So our current MCS is high, but it drops into a low MCS. My block error rate, or my blocks, the number of PRBs that are assigned, are very low, somewhere in the area of 1 to 3. And then my block error rate is very high. We're very high block error rate at this point. So at this point, we are going to trigger the subscriber going into TTI bundling. Okay, this is also noting that this particular drive test tool did not do proper calculation of the TTI bundling due to the fact that only one ACRNAC was sent out of the 4 subframes in the bundle. And we'll talk a little bit more to that because there's some functionality we still need to see with the TTI bundling. So here we go into TTI bundling mode. We have all conditions, all three conditions are met. I'm in TTI bundling mode. That triggers the handover, and now we start moving in. Now, it doesn't mean we will leave TTI bundling mode until, in fact, we will not leave TTI bundling mode until we have reached a threshold. So here our blur threshold has occurred. We go into TTI bundling mode at this point. So looking at it from the UE's perspective, and actually I was talking to a drive test person and they said, this is a really hard feature to prove because you have to have exactly the right conditions for it to happen, where the blur is low enough, where the MCS is low enough, the block error rate is high enough, and the number of PRBs is low enough for us to go into the TTI bundling. So we've reached the TTI bundling threshold here. We reached it here. The second line, really, the first line with the bad calculation from the drive test tool, and we go into TTI bundling.
More to tell about these traces here, otherwise I think we might want to look at the signaling that is going on for this feature.
Sure. The signaling on the feature is really a good situation. So here we're looking at our RRC connection. So TTI bundling mode is conditions are accepted. So we got to those thresholds. The eNode B will then send an RRC connection reconfiguration message, which in this case is a handover command to itself, to the same cell. That means, and it will come out with a dedicated preamble, which the subscriber will use as a dedicated preamble in using the Pratch. We then send the random access response for that preamble, and then we reschedule transmission for message 3. So this is all the preamble transmission. This is all to do the handover, the intra-cell handover. We then go, from then on, message 4 and beyond becomes the TTI bundling mode. So we perform everything in TTI bundling mode from here on. Because it was a dedicated transmission here, we probably won't see the contention resolution message, but we will see the RRC reconfiguration message at this point. Then we'll have an RRC reconfiguration complete coming back, and all of our uplink grants will now have the subscriber transmitting in TTI bundling mode.
All right, so that's a nice general picture. Do you have some more interesting details?
Okay, just so that you see what the messaging is. In the messaging, in the Mac main configuration, you're going to have a TTI bundling field. This TTI bundling field will be set to true. We will have a new set of maximum hybrid ARQ transmission parameters for TTI bundling. So we'll have, it'll be different than the regular TTI, non-TTI bundling mode. We will deactivate discontinuous reception in the uplink. We will not necessarily show all of the other parameters, but we'll change the parameters that are necessary in that RRC connection reconfiguration message. So looking at the trace a little bit better. So here is the RRC connection reconfiguration message that comes out to the subscriber. It is an intra-cell handover. Here's the UE's identity for the new official CRNTI, even though it'll probably be the same one. And the TTI bundling is set to true, and we have a new maximum number of hybrid ARQ retransmissions in that message.
All right, so then we change into bundled transmission, and we can maybe also look at how it looks on TTI level then?
So here's our TTI. Now, one of the things that you have to understand is when we create a transmission within LTE, we normally create 4 separate revisions. So we take the packet plus all of the bit errors, the bit rates and all that, and we divide it into 4 segments called revisions. Now, under normal circumstances, only one revision is sent before I get an ACK or an ACK. In TTI bundling mode, I don't. I send revision 0, revision 1, 2, 3. I send all 4 revisions sequentially, 4 separate TTIs. I send all of them together, and then I get one single ACK-NACK. Oh, also, because the subscriber's in TTI bundling mode, I am going to assign one PDCCH resource to give it that assignment. Actually, you see it a little bit better further on here in TTI 13, in TTI number 13. Here's the grant, and then you see the revision transmission. So you send 4 transmissions sequentially, but only one TTI. Now, the difference between this and the uplink packet segmentation is in uplink packet segmentation, I would send this one for Rev 0. I would send a grant here for Rev 2, a grant here for Rev 3. Oh, but in TTI, in the uplink packet segmentation, all of these would be Rev 0 or Rev 2 or Rev 3 or Rev 1. In this case, I am sending all possible versions of the packet. So the probability is if there is an error, the subscriber should be able to decode it using all 4 revisions. But if they can't, they have the option of an ACK, and then we will retransmit all 4. And this will be an ACK or an ACK, and then a retransmit again. So this is a retransmission of the entire bundle.
Okay, well, this highlights quite nicely how we save on PDCCH resources in comparison to this other feature. Do we have any kind of restrictions in terms of how the channel is configured? For instance, modulation?
The modulation will always be set to QPSK. The number of PRBs assigned will always be 3. So we can use higher MCSs within QPSK. So we can actually use MCSs that are like 10, 11, 12, which are normally 16 QAM, but they would be in QPSK. It just means fewer and fewer parity bits that would be used in the transmission. So a transmission, a whole transmission bundle, so that's 0, 2, 3, and 1. So all of these would consume a total of 12 PRBs. 3 here, 3 here, 3 here, and 3 here. Always set to 3. And the modulation will always be QPSK in our implementation with TTI bundling.
Okay, do we have some more details about how retransmissions are handled?
Sure. In a retransmission, so we have the retransmission. The retransmission, again, I transmit the original. I get an ACK. I have the scheduling of the PDCCH 5 subframes later for the retransmission. Again, I will retransmit all revisions. Now, here's the one difference. This is one header. So I'm going to have one PDCCH header for this TTI bundling. So it's a little less overhead. So I'm going to be using that, or doing the retransmissions. Every time I retransmit, I will have, and this is the 3rd retransmission. What we're looking at is in that retransmission, and we will take, basically, if I'm sending you a fax, I send you the fax 4 times. If it happens to be a noisy line, you don't hear it, you're able to rebuild it with the 4 pages. If not, you can rebuild it with the next 4-page retransmission. That's the idea, is we can rebuild utilizing the portions of the page, copy or cutting and pasting the whole fax together. Well, that's what we're kind of doing with this hybrid ARQ and all of the transmission, all of the sub-revisions. So you have a complete picture every time we retransmit. But what's interesting is, when we look at that, we talked about this bundling. If we set that bundling to 12, now what is 12? That's 4, 8, 12. If I set the bundling to 12 and then I compare it, so 4 transmissions, 8 transmissions, and 12 transmissions. If I set it to 12 transmissions, it actually improves my link budget by about 2.5 dB or 2.3 dB. Now, why? Because what it is it's giving me a better chance to recuperate throughput based on the hybrid ARQ. Now, you say, what's it gaining against? It's gaining against the non-TTI bundling mode, because in the non-TTI bundling mode, I would have the transmission, single TTI, 3 subframes later, I'd have the NAC. Then I would have another retransmission and then retransmission, but I would only have pretty much by the 12th transmission here, I would really have only transmitted that bundle or that packet once, twice, 3, 4 times, where we have transmitted the packet or all of the revisions 3 times in that same packet area. So we actually have a gain of TTI bundling because of TTI bundling. Okay, link adaptation. How does this interact with the link adaptation that we have? Because we are still going to be adjusting our MCS using outer loop link adaptation. We will go ahead and trigger the TTI bundling. Is TTI bundling enabled? Am I going to do adaptive transmission bandwidth? If I am, yes. Then I go into the slow ATB and PRV adjustment functionality. And yes, this is exactly where TTI bundling will be working. I'm working in the TTI bundling, but this is, so the subscriber is going to have a slightly different link adaptation because it's using TTI bundling from the rest of the UE. So it's going to have an adjustment to this part here because the bandwidth in TTI bundling is limited to 3 PRBs. It's hard limited, and the MCS are the order of modulation is limited to, in the MCS here, the order of modulation is limited to QPSK. But other than that, it's going to continue using the same structures, except those parameters for that specific UE are going to be set, hard set, during its TTI bundling, during its TTI bundling functionality or mode, being in the TTI bundling mode. So let me go on. Let's see what I mean. So remember, we said that the UE is fixed to 3 PRBs, okay, but we can actually use an MCS. So the MCS is set to 3 PRBs, so that's the maximum size. But the TTI MCS range index can be from 0 to 24, but notice that in this case, the order of modulation is all the way is 2. What that means is I use fewer and fewer bits in my transmission for me to be able to perform it. Now, there is one little point. Notice we really can't use 0 and 1 because of the parameter that we set, which is the minimum uplink transport block size is 104. really we're going to have to start at modulation coding scheme 2, which is the first MCS that has a transport block size that is greater than that minimum transport block size. So really, we're only going to be able to use 2 to 24. That should be fine in what we do in our with the transmission. Now, because it is only 3 PRBs that are in use, we probably don't want to use higher throughputs using TTI bundling.
And that tells us that this is related to low-rate services like voice again. In summary, we can say that link adaptation is somewhat restricted in comparing to non-TTI bundling mode. Now we have seen how TTI bundling is started and how it works once in operation. How do we get out of it when the conditions improve for the user?
Oh, I think once you go into TTI bundling, you stay in jail. No, not really. You're right. That's a very good question. That's a great question. So here we do. What we have is when the SINAR comes above the SINAR threshold, when the average uplink SINAR is greater than or equal to the SINAR threshold, which is what triggered the going in, or is one of the conditions that triggered going in, once we exceed that SINAR threshold, we will leave TTI bundling. Again, we will then need to do an intra-cell handover to move back into normal transmission mode.
Well, that looks straightforward. I guess you also tell us about the signaling in relation to that procedure.
So here's our RRC connection reconfiguration. So we'll send an RRC connection reconfiguration message to the subscriber. By the way, signaling does not use TTI bundling mode. So it's in the downlink shared. The control information is not sent in TTI bundling mode. So if you look at here, it's a single message in the TTI bundling. And here we send a RRC connection reconfiguration to the subscriber. The subscriber will then perform the regular RATCH functionality, the random access, and come back in. And in that RRC connection reconfiguration, it will change it to TTI bundling false, which means leave TTI bundling mode. And when I get that RRC reconfiguration complete after my UE, so here's my RRC connection reconfiguration message is complete. That's where the subscriber says, yes, I'm out of TTI bundling mode. Here's where the command came. Then I have the RRC connection reconfiguration complete, and the subscriber is now out of TTI bundling mode. Although we have to do the intra-cell handover procedure to switch modes in the end.
Okay. Do you have some traces showing this part as well?
Okay, so looking at it, the subscriber goes into TTI bundling mode at this point. So in here, we're looking at the MCS index. Notice that the MCS index goes up. This is showing that I'm getting more throughput. Looking at the same in the transport block size, and this is looking at transport block size in bytes, we're going to have the minimum transport block sizes here. We meet the criteria to go into TTI bundling at this point, meet the TTI bundling, so we started TTI bundling, but notice that our throughput is higher in bytes. Our transport block size is higher in bytes during TTI bundling. At this point, the MCS is high enough, and we can leave TTI bundling mode here, or we performed a handover and went somewhere else. So looking at the SINAR for the same condition. So the TTI bundling is started because our SINAR dropped, and then we get to TTI bundling. Our SINAR really doesn't change. But the SINAR, once the SINAR is above the threshold, so it reaches a higher threshold here, the average SINAR for all of this is high enough that it exceeds the SINAR threshold, that's when it triggers us getting out of jail free. So we can escape back to the non-TTI bundled format.
On the network side, what options do we have to follow this up? I already see some counters that relate to TTI bundling.
Yeah, there are counters that are in TTI bundling. So we have the TTI bundling mode, the average number of subscribers in TTI bundling. We have the number of bundling grants. Okay, how many times did we hand a TTI grant for bundling? So this is actually resources assigned in the upline. How long did we have the subscriber in TTI bundling? So there's actually three. We have a short one, we have a medium one, and we have a long one. The short one being less than a quarter of a second. The medium one is between a quarter of a second and 5 seconds, and the long one is greater than 5 seconds.
I guess those have also been turned into some recommended performance indicators.
Yes, they have. So we have the TTI bundling user ratio. I love trying to read the formulas. But yes, so we have the TTI bundling ratio. What's the ratio of subscribers in TTI bundling mode to the regular subscribers? And particularly we look at QCI1, because QCI1 is where we have configured in Nokia, we have specifically focused on the voice call and the small amount. It also is our maximum compression for the small resources, or for the small packet like voice. We also have what is the ratio of UEs that are in short mode to all of the UEs that are in TTI bundling mode, medium and long, so we can figure out where are they just staying for a very short period of time, or are they staying for extended period of times in TTI bundling mode.
All right. Have you seen those at work somewhere? Practical examples. I see them coming. Very good.
Here's a great example. So you can see. Okay, so here's the number of bundling grants that we receive at different times. This is saying, okay, the sum, the blue line being the sum of the bundling grants, of all of the bundling grants. So you can see that it does get used. It isn't always used because it's in poor condition. This is those really points of condition. Remember, the subscriber has to have TTI bundling in one of the bearers for it to even use the bearer. So if we have subscribers that don't have that kind of bearer, they wouldn't be going into this TTI bundling. This is showing an example of what we had in a test case that we were given, showing where the grants were. So we don't have a lot of grants, but the total number of TTI bundling grants being the blue here, and the number of UEs, this is the number of UEs in TTI bundling. So there's this one particular area where were having TTI bundling. And in some ways, this is a good place to focus on to try to see if we can optimize coverage at a different time. Because TTI bundling does consume more resources. It doesn't consume as much as uplink packet segmentation, but it does consume more resources. So looking at retention time, same particular one. Now we're looking at how many subscribers were in medium. We really don't see any short retention time here, unfortunately. The blue, which isn't visible. The medium is red. So most of our subscribers stayed in medium, but then there was a few subscribers that actually stayed in TTI bundling mode for a long time, for longer than 5 seconds. Now, how do we terminate? How did they terminate this? The probability is they terminated by performing a handover and leaving the cell. So 2 ways to get out of TTI bundling mode. I get into better conditions in my cell, the SINAR gets better, or I get a handover into another cell. And that's really the idea of TTI bundling, is to provide better coverage for the subscriber until he gets to the edge of the cell and can perform a full handover to another cell that has better coverage. And it's not in TTI bundling mode.
Okay, very nice. So then we could look into some numerics for the link budget impact as we are looking for coverage improvement.
Oh yeah, coverage improvement is really key. So what we're looking at is, I was kind of trying to describe it earlier, but if I have a transmission here in normal mode, this is without TTI bundling, I have one single revision transmitted here, then I retransmit it here, then I retransmit it here, and then I'd retransmit it here. Okay, so here in this particular example, I have 3 different transmissions, 3 different transmission blocks that are sent in the uplink versus the 8 that I have here. Okay, so let's look at this. The time it takes for me to transmit 3 blocks. So I have the initial transmission, I have 2 retransmissions. The time it takes me is 16 transmissions versus the time it takes for me to get through and transmit here in the same period of time. I have 4 transmissions. This is showing where my retransmission is set to. In TTI bundling, in the same period of time, I would have of transmitting 7 of these. In TTI bundling, I actually can transmit 16 transmission blocks. So in 7 of the regular TTIs, I can transmit 16 of in TTI bundling mode, 16 transport blocks. That gives me the 16 here over 7 transmissions, and the formula is 10 log 16 over 7, which gives me a 3.59 dB gain. Okay, it's slightly different than the one that we commented earlier. It's because this is using a longer TTI bundling period instead of, so this is looking at a 53 millisecond delay budget versus the 12 millisecond delay budget that we saw that was on earlier, that I mentioned earlier, that had a 2-point-something dB gain. But this does affect our link budget. So if we're looking at our link budget and we're looking at our channel model portion of the link budget, we're looking at the different aspects of it. If we have TTI bundling enabled in the uplink, okay, if we have TTI bundling enabled in the uplink, it affects the SINAR at our cell edge. It does affect our receiver sensitivity, and the maximum allowable path loss is increased because TTI bundling in open loop MIMO in this case. So we're assuming open loop MIMO, we're interference aware scheduling, and we have 1 dB of interference margin. We are able to adjust our throughput, our SINAR at cell edge. We have a gain of the SINAR at the cell edge of, in this case, they're showing 3.3 for, this is the required SINAR for cell edge for the uplink because we have enabled TTI bundling. What happens is our SINAR requirement improves because we have actually added the TTI bundling. So the gain, the interference gain, we have better sensitivity because we're getting 4 retransmissions all together. So that gives us a bundling gain here in the receiver sensitivity, thus giving us a higher gain on higher allowable path loss, so that our actual received signal will be better.
Okay, very well. I think this completes our material on TTI bundling.